I am Ijaz Ahmed. In this lecture, we will discuss about even and odd permutations. Then we will study the alternating group. So we start by defining what are even and odd permutations. So we write here the definition of an even permutation. A permutation alpha in Sn is even if it can be written as the product of given number of transpositions. Since we have already seen that every permutation in Sn can be written as a product of disjoint cycles, and we already know that every cycle can be written as a product of transpositions, so it means that every permutation in Sn can be written as the product of transpositions. So now if the number of transpositions in this permutation Sn, in this permutation alpha is even, then we call this alpha to be an even permutation. Similarly, we can define an odd permutation. So in this language, we can say that a permutation alpha is odd if it can be written as the product of odd number of transpositions. So that is the definition of an odd permutation, but we will just write here a permutation that is not even, is an odd permutation. Okay, so these are the definitions of even and odd permutations. Let's take an example here. For example, let alpha is equal to 1, 3, 2, 4. Now this is a permutation in S4. So actually this is a 4 cycle in S4. Then we can write, then in the previous lecture we had already seen that this alpha can be written as a product of transpositions like this. It is 1, 4 into 1, 2 into 1, 3. So therefore the number of transpositions in this alpha is equal to 3, that is odd. So this means that this implies alpha is an odd permutation. So therefore alpha is an odd permutation. Now similarly, let's take one more example, beta, which is equal to 1, 2, 3, 4 into, suppose, 2, 1. Then this permutation is actually the product of two cycles. Now this can be written as 1, 4 into 1, 3 into 1, 2, then we have here 2, 1. So therefore the number of transpositions in this permutation is 4. So this means that this implies beta is an even permutation. In fact, in this beta, we can see that 1, 2 into 2, 1 is an identity. Therefore, this beta is actually 1, 4 into 1, 3, but still the number of transpositions is 2, so this beta is an even permutation. So in fact, we can see here that a given permutation can have many representations as the product of transpositions, but everywhere the number of transpositions will be either even or they will always be odd. If one of the representations has an odd number of transpositions, then all the representations of this alpha will have odd number of transpositions. And similarly, if one of the representations of beta has even number of transpositions, then all the representations of beta will have even number of transpositions. So it means that this beta is an even permutation, and therefore this alpha is an odd permutation. Now we make one more definition here just for the sake of using the language. Parity. The parity of a permutation, the parity of permutation is defined as whether a permutation is even, whether a permutation is even or odd, is even or an odd permutation. So whether a permutation is even or odd, we call that evenness or oddness of a permutation as its parity. Now here we make certain small results. Let's call that result a proposition. If alpha and beta are two permutations in Sn such that alpha and beta have the same parity, if alpha and beta have the same parity, then the composition alpha beta is an even permutation. So if we have two permutations in Sn that have the same parity, then their product is always an even permutation. Let's call this as part number 1. Then the second part for this proposition may be written like this. If alpha and beta belong to Sn, have different parity. If two permutations alpha and beta in Sn have different parity, then alpha into beta is odd. So whenever two permutations have an opposite parity, then their composition is always an odd permutation. Let's make one more statement here. The permutation, the permutations, permutations alpha and beta, alpha beta inverse have the same parity. So this third part says that the two permutations alpha and alpha beta inverse always have the same parity. So the parity of this alpha beta inverse just depends on the parity of the permutation alpha. Now let's proceed towards proving these things. The first part is we are given alpha and beta are having the same parity, then we have to show that alpha beta is an even permutation. So first assume alpha and beta are even. So this means that alpha can be written as a product of even number of transpositions and beta can be written as the product of even number of transpositions. So this means that alpha is equal to, suppose, product of even number of transpositions and similarly beta is equal to product of even number of transpositions and so on. So this means that therefore alpha into beta, this will be equal to, suppose if the number of transpositions here is equal to m1 and the number of transpositions here is equal to m2, whatever are the integers m1 and m2, then 2m1 is even and 2m2 is odd, then alpha into beta will be equal to product of 2m1 plus 2m2 number of transpositions. So this means that now since 2m1 plus 2m2 is an even number, therefore alpha beta is again an even permutation. So therefore if alpha and beta are both even, then alpha into beta is even. So this means that if alpha and beta have the same parity as even, then alpha beta is an even permutation. Now similarly we next assume alpha and beta are odd permutations. So in this case what happens? So this implies alpha is equal to product of 2m1 plus 1 transpositions. Similarly, beta is equal to product of 2m2 plus 1 transpositions. So then alpha into beta, this will be equal to product of 2m1 plus 1 then plus 2m2 plus 1 transpositions. And again we can see that the sum of two odd numbers is always an even number. So this means that if alpha and beta are both odd permutations, then alpha into beta is again an even permutation. So therefore finally we conclude that if alpha and beta have the same parity, it means that alpha into beta will always be even. Now similarly we can proceed towards the second part. Second part is alpha and beta have opposite parity. Opposite parity. So first assume if alpha is even and beta is odd, then alpha will have 2m1 transposition suppose, and similarly beta will have 2m2 plus 1 transpositions if beta is odd. So this implies alpha into beta has 2m1 plus 2m2 plus 1 transpositions. Now since the sum of an even number and an odd number is always an odd number, therefore in this case alpha into beta will be an odd permutation. And similarly if we choose alpha to be an odd permutation and beta an even permutation, we will arrive at a similar conclusion. So we can proceed toward the third part, alpha and beta alpha beta inverse. Beta alpha beta inverse. Now here we can see that suppose first case 1, if alpha is even, then what we can say about beta alpha beta inverse? So if alpha is an even permutation, suppose beta is even, then all the three permutations are even, so the number of transpositions in the product beta alpha beta inverse will be even. So therefore in this case, beta alpha beta inverse will be an even permutation. Now suppose that beta is an odd permutation. Now then beta will have odd number of transpositions, beta inverse will have odd number of transpositions, and since alpha has even number of transpositions, so beta alpha beta inverse will have odd plus even plus odd number of transpositions, that is again an even number. So in these both the cases beta alpha beta inverse will have even number of transpositions. So this beta alpha beta inverse will be even. And similarly case second, if alpha is odd, this case follows similarly. Then beta alpha beta inverse will be odd. So this was some relations about the parity of the permutations. Now we discuss. Now let's write the set of all even permutations. Let us denote this set by an. So this an is the set of all even permutations from the symmetric group Sn. Then an is a subset of Sn. Then we can easily see that if an is the subset of all even permutations in Sn, if alpha and beta belongs to an, then alpha and beta are even permutations, then alpha and beta are even permutations. So this means that alpha has even number of transpositions and beta has even number of transpositions. This clearly implies beta inverse is an even permutation. And in fact, alpha inverse is also an even permutation. So actually, when a permutation is even, then its inverse will again be an even permutation. So therefore, if beta is an even permutation, therefore beta inverse will also be an even permutation. So here we have actually three permutations, alpha, beta, and beta inverse, which are all even. Then this clearly implies alpha beta inverse is an even permutation. So this, what does this imply? This implies that an is not just a subgroup of Sn, subset of Sn, but this implies an is a subgroup of Sn. Okay, so we have seen that an is a subgroup of Sn, so we can make this into a statement in the form of a result, or let's write it like a theorem. The set of all even permutations the set of all even permutations denoted by an is a subgroup of Sn. Is a subgroup of Sn. Now we proceed towards one more theorem, which is actually one nice theorem here. An is a normal subgroup of Sn. An is a normal subgroup of Sn with order of An is equal to n factorial divided by 2. So this means that An is actually a normal subgroup of Sn of index 2, because order of Sn is equal to n factorial. So now let's proceed towards the proof. So we already know that we have from the previous result An is a subgroup of An is a subgroup of Sn. So we only need to prove that An is normal and the order of An is n factorial by 2. Now for doing this, let G is equal to 1 minus 1 be a group under multiplication. This is a group under multiplication. In fact, this is a subgroup of the set of real numbers, subgroup of a group of real numbers under multiplication, subgroup of the group of non-zero real numbers under multiplication. So we take this G as the group 1 and minus 1 as a group under multiplication. Now define the mapping. Suppose psi from Sn into G by, suppose psi of alpha is equal to 1 if alpha is even. So if alpha is an even permutation, then we define psi of alpha is equal to 1, and this is equal to minus 1 if alpha is an odd permutation. Then it can be easily seen that then psi is a homomorphism. And what we mean by psi is a homomorphism, that is psi of suppose alpha beta is always equal to psi of alpha into psi of beta. And this can be easily checked by this definition. If suppose alpha and beta are both even permutations, then alpha beta is an even permutation, so alpha psi of alpha beta will be equal to 1. Psi of alpha will also be 1 and psi of beta will also be 1, so therefore in all cases, therefore this left hand side will be equal to right hand side. Now if alpha and beta are both odd permutations, then alpha beta is an even permutation, so left hand side is 1, and psi of alpha is minus 1, psi of beta is minus 1, and minus 1 into minus 1 is plus 1. So again, psi of alpha beta is equal to psi alpha into psi beta. And lastly, if alpha is odd and beta is even, then alpha into beta is an odd permutation, therefore psi of alpha beta is minus 1. But similarly here, one of the psi of alpha will be minus 1 and psi of beta will be equal to plus 1. So this means that 1 into minus 1 is minus 1. So therefore in all cases we can see that psi is a homomorphism. And we can easily see that psi is an onto homomorphism. Now every element, now the G has two elements, 1 and minus 1, and the pre-images of 1 are the even permutations from Sn, and minus 1 has its pre-images as the odd permutations of Sn. So therefore this psi is an onto homomorphism. So clearly psi is an onto homomorphism. So therefore, a fundamental theorem of homomorphism, thus by fundamental theorem, fundamental theorem of homomorphism, Sn upon kernel of psi will be isomorphic to G. So now the new term from this fundamental theorem of homomorphism comes, that is the kernel of phi. Now let's try to see what is this kernel of phi. By definition, this kernel of psi will be the set of elements S belonging to Sn such that psi of S is equal to 1. So then, but by the definition of the mapping psi, we can easily see that this kernel of psi now contains all those permutations whose image is 1. So that means it contains all the even permutations. So actually this kernel of psi is the subgroup Sn. So therefore we have Sn upon An is actually isomorphic to G, because this kernel of psi is the group, is the subgroup An. So this, therefore we have proved that Sn by An is isomorphic to G. So this implies that, and in fact uh, kernel of a homomorphism is always a normal subgroup. So this conclusion, when this kernel of psi is equal to An and psi is a homomorphism, so this statement actually says that An is a normal subgroup. So therefore we can add it here. So this implies An is a normal subgroup of Sn. Therefore we have Sn upon An is isomorphic to G. So this implies order of Sn upon order of An is equal to order of G. And now We know that order of G is equal to 2 and order of Sn is equal to n factorial. So this implies order of Sn upon order of An is equal to 2. So this statement actually says that San is a subgroup of Sn of index 2. But from this we can also conclude this implies order of An is equal to order of Sn upon 2, which is equal to n factorial upon 2. So let's make the conclusion here now. An is a normal subgroup. An is a normal subgroup of Sn of index 2. With this, we further add that, actually we want to add that the subgroup An, the subgroup An is called the alternating group. So therefore alternating group is the group of all even permutations, and it is the normal subgroup of Sn, where Sn is a symmetric group on n symbols. So with this we conclude this lecture.